Hey, what's up? This is Madan here, and I have come up with your very next video. And if you have watched my previous video, you probably know that I'm doing redox reaction. And I want to say something, what happened. I've seen people are really, contributing towards online, coaching. But what I have in difference is that, giving you each and every topic from a chapter. Though I haven't done so many chapters, but whatever chapters I have done, they are absolutely based on your syllabus, based on the sequence of topic you have, right? Except a few. So I've been, telling you in my previous video as well that in case you are interested to make, your study without visiting anywhere, this might be possible watching my videos. So what you have to do is to come to my channel and open that playlist. And if you find there is a chapter that's going to be useful to you and you need to study that, just open it and watch it. Based on the observation, keep making your notes, trying to get it through the facts. And in case you have problem, don't forget to let me know, because only then I'll be able to make some changes possibly you need and I need also, right? Anyway, this is going to be the last video of redox reaction where I'm going to talk about the, calculation of oxidation number where the formula cannot be applied. Because in so many cases, there's some structure, there's a molecule of compound where you cannot apply the formula. And what the formula was? The formula was arithmetic sum of oxidation number of all the atoms is going to be equal to the magnitude of charge. So this is not applicable everywhere. So I'm going to get you through another method which is based on the structure of the molecule. So if you know the layer structure of the molecule, you will definitely understand how you can find out the oxidation number of almost all the species you want, right? So this is what the topic is. So let me write that. Before that, I want to repeat a little bit of what I have done earlier. The first method to find out the oxidation number is the formula. And what the formula is, arithmetic sum of all the atoms, arithmetic sum of all oxidation state of all the atoms are equal to magnitude of charge. Magnitude of overall charge. So this was the law. Let me take you the example, and so that you remember exactly what I tried last time. So suppose I am trying to calculate the oxidation number of Mn in KMnO4 on the basis of the formula. If I am trying to find the oxidation number Mn, this is going to be like +1 plus x plus 4 into -2, because you do know that the oxidation number of oxygen is -2. And equal to 0, because this compound is overall a neutral one. So the magnitude of overall charge is 0. So this is coming out to be x equal to 7, right? So this was the law. Let me give you another example. Another example is that, H3PO2. This is the second example, H3PO2, and you are interested to find the oxidation number of phosphorus. So it's going to be like 3 into 1 plus x plus 2 into -2, because oxidation number of oxygen is -2 equal to 0. So what x is coming out to be? This is going to be like +1. So this is coming out to be +1, right? But taking the third example will help you to understand that why this formula is not applicable everywhere. I'm taking the next example, and there you will understand why this formula is not everywhere applicable, right? So take the example of Ki2, Ki3. So Ki3 I'm trying to understand what the oxidation number of potassium. So what I will do, x plus 3 into minus 1 equal to 0. So x is going to be plus 3. Now there is the problem. This is not possible. This is not possible. Why this is not possible? Because potassium is an alkali metal member. An alkali metal have only plus 1 oxidation state, and they have only 1 electron in their outermost shell. So they can only have plus 1. If you remember the rules I have made you in the previous, maybe the second last or third last, I don't remember. So this is not possible. Now the question is, what is exactly going on here? So I tell you what exactly, this is. Actually, Ki3 is made up of, there are two compound, Ki plus I2. So in Ki, there are two species, Ki plus I2. So in I2, the oxidation number is going to be 0, and in I, it's going to be, minus 1, and for K, it's going to be plus 1. So the oxidation number of K in this particular case is plus 1. Any atom bonded to itself has oxidation number of 0. This is called uncombined state. So that's why iodine is having 0 and the potassium is coming out to be then plus 1, right? Take another example here. So I'm taking this fourth example. The fourth example is of Fe3O4. You know what? In Fe3O4, if you use the formula, this is going to be like 3x plus 4 into minus 2 equal to 0. So x is coming out to be, minus 8 plus 8, 8 by 3. And this is called average oxidation state. This is called average oxidation state. Right? And if question is what is the average oxidation state of Fe in this compound, this might be the answer. Otherwise, if the question is what is the oxidation state of iron in Fe3O4, this will be wrong. This is not going to be accepted. This will be absolutely wrong. So what is the actual oxidation state? Actually, Fe3O4 is made up of Fe2O3 plus FeO. When these two oxides combine, it forms Fe3O4. So what's happening here? The oxidation number of iron is going to be plus 2, and there is going to be, plus 3. So what that means, that oxidation number of iron is equal to plus 3 and plus 2 here, plus 2 in this particular compound. So you have to remember that there are some exceptions. You have to understand that, right? Okay, let's take another example. Now I'll be taking structural, structure-based oxidation number. So take first example, H2SO4, right? H2SO4. If we try to solve it, in the earlier format, this is going to be like 2 plus x plus 4 into minus 2, that's equal to 0. So x will be coming out to be 6 here, 6. Now draw the structure and see what this is about. So sulfur is here, sulfur is having 2 peroxide linkage and 1 hydroxide linkage. This is the structure of H2SO4, right? Now, I tell you something very important. You know what? Even structure is quite, interesting to find out, oxidation number. But this also becomes sometimes difficult because not every structure is that simple, right? So you have to be, make yourself, into a mode where you prioritize how you're going to find out the oxidation number, right? So sometimes you have to use structure-based oxidation number calculation. Sometimes you have to use this particular method. So let's find out how 6 is coming out to be. I would say for a double bond, an atom is awarded minus 2. So the oxygen will have minus 2 and sulfur will have a plus 2. Similarly, there will have plus 2 and oxygen will have minus 2. Now, but there is a single bond here. So minus 1 and again a plus 1 here. Then again here minus 1 and plus 1 here. Hydrogen will have a plus 1, hydrogen will have a plus 1. So what X is coming out to be here? X is coming out to be 2 to 4, 5 and 6. So X is also 6 here. Right? So let me repeat one thing. For a single bond, an atom which is more electronegative is awarded -1 oxygen state, and the other one which is less electronegative is awarded +1 oxygen state. So that way there are two bonds, so that's why I'm taking -2 here. You can see out -2, there is -2. So for one bond it's -1, for two bond it's -3, right? So this is how you can find out the oxygen state of H2SO4. I'm taking another example here, Br3O8. Now how this looks like, there are three bromine, and all of them have peroxide linkage. All of them have peroxide linkage. So like I said, this is going to be -2, there it is +2, -2, +2, -2, +2. Now concentrate here. Bromine is bonded to bromine. So it's going to be 0 and this will be 0 again. If you remember, an atom is bonded to itself, then the oxidation number is awarded 0. So that's why it's 0, right? Similarly, so for this one, the oxidation number is coming out to be +2, +2, +2. So it's going to be +6 here, right? Find out here. So that's -2, there is -2, right? And there is 0, there is also 0, there is also 0. So for this bromine, the oxidation number is coming out to be 4, right? And this will be exactly same. So this will be also like oxidation number +6, right? But if you use the formula, let me write the answer here and then I will use the formula. So oxidation state of bromine is +6, +4 and +6, right? Okay, now based on the formula, let's see. Suppose it's 3x plus 8 into -2 equal to 0. So x is going to be +16 divided by 3. And this will be average oxidation state. This will be average oxidation state. So for this molecule, you cannot use this particular formula. You cannot use this formula. You can only use structure-based, method to find out the oxidation number. So I've tried to, to help you out. If this has been really useful. Do let me know, right? I'm taking furthermore example. So take H3PO, H3PO2. And this is going to be interesting. You know what? Phosphorus structure is in H3PO2 is like, there are two oxygen here. So one double bond and one oxygen with hydrogen bond, and other two hydrogen are bonded to this condition. So this is a H3PO2. Now, I would say something very important. A double bond is called peroxide linkage, where oxygen is given -2, but in single bond it is given a -1. But in case you have problem, with all that what I just said, I would say in very straight way, in very simple way, for a single bond, -1 and +1, that is the oxygen state. For a double bond, +2 and -2. So how? You do know that oxygen is more electronegative than phosphorus. So this one will be -2, phosphorus will be +2. Do I have to repeat it? Oxygen is more electronegative, so this will be -2 and this will be +2. There is one bond here, so this will be -1 and there will be +1. There it's +1 and -1. Why there is -1? Because phosphorus is, more electronegative than hydrogen. And there is again +1 and -1. So what we come out to be here, and there is going to be +1. So we have, here for phosphorus, the oxidation number is going to be, like -1, okay, +1, -1, again -1, +1. Is it going to be messy here? Let's add them together. So there are 3, +1 and -1. This is going to be +1. So that's the oxidation state. Take another example. I'm taking next example. So the second example I'm taking is H3PO2. PO4, make it 4. So what the structure is this time? This is phosphorus here. There are 4 oxygen, 3 hydrogen, and that's going to be like, oxygen, oxygen with hydrogen, oxygen with hydrogen, and oxygen with hydrogen. So this is the structure. Let's count again. Oxygen is having a single bond. So what will happen? It will have a -1. There it will have a +1. There it will have a +1. There it will have a -2. But this will have a +2. Again -1, +1, +1, and -1, +1, and +1. I hope it's not messing up. For every bond, what I'm trying, for every bond, the atom which is more electronegative, I'm awarding -1, and the one is having less electronegative, I'm awarding +1. If there are two bonds, if there are double bond, I'm awarding -2 for more electronegative and +2 for less electronegative. So this way, the total of oxidation number for phosphorus is going to be, let me count here, +2 and +3. So this is going to be +5 here. Right? So I'm taking third example. This time I'm taking a bit, bigger molecule. And this molecule is, if this was fourth example, H2SO7. This is called oleum. And oleum is also called disulfuric acid. Disulfuric acid. Forget about the name. Let's get back to the structure. This has a complex structure. So sulfur, oxygen, hydrogen, oxygen, sulfur, oxygen, hydrogen, and both of these sulfur are having 2 peroxide linkage each. So this is the structure of, oleum, right? Let me count this. 2 hydrogen. Okay, now 1, 2, 3, 4, 5, 6, 7. Yeah, that's the structure. Let's go for that. So suppose this is S1 and this is S2 here, right? If this one doesn't confuse. So O is having a -1, hydrogen is having a +1. This H is having a +1, O is having a -1. Now let's come with this. So O is having -1, S is having +1. Again, S is having a +1, O is having a -1. There it is -2 and there it is the +2. -2 and +2. -1 and +1. Right? From all sides I have mentioned the oxidation number of sulfur. Right? Okay, similarly, so let's count out what is the oxidation number for S2? This is going to be +2, +2, +4, +5, and +6. So this is going to be +6. So this one is going to be exactly the very same. So S1 is also having a +6. I hope you have started understanding how in a structure the oxidation number is calculated. For every single bond, the atom with more electronegativity is awarded -1 and the one with less electronegativity is awarded a +1. So that's how I'm, trying to get it.